Use the rules we learned in the last segment to analyze some more complex circuits. We're going to start with a very simple one. I've got a 10-volt power supply. I've got a 1,000 ohm resistor. And when I take this 1,000 ohm resistor and I hook it up to this power supply, 1,000 ohms, 10-volt power supply, what current in milliamps do I get in this circuit? We'll give you some choices. Well, this is just a question for Ohm's law. The current is equal to delta V divided by R. 10 volts divided by 1,000, 0.01 amps, 10 milliamps. We get 10 milliamps. And in fact, if we hook this up to a meter to measure the current, what we get is 10 milliamps. 10 volts, 1,000 ohms. I get 10 milliamps. But now I'm going to make some changes to this circuit. I'm going to make some changes to the circuit. And what I'm going to do is disconnect this resistor from the power supply. Then I'm going to connect a second identical resistor in series with it. So this is a simple series circuit. And now I have a 10-volt power supply through a current meter, through one resistor, through a second resistor, back into the power supply. Okay, so that's my setup that I have right here. And I can measure the current that I'm seeing right here. But first, I have a question for you. 10 volts here, there's no voltage across the ammeter, no voltage. So let's assume no voltage here. 10 volts, what is the voltage across each one of these identical resistors? We'll give you some choices. Think about it. These are identical. It's 10 volts from the power supply. It's 10 volts right here. It's 0 volts right here. That's the negative end of the power supply. 10 volts, 0 volts, two identical resistors. What's the voltage at the midpoint? 5 volts. And if we measure, the voltage right here is 5 volts. So each one of these resistors now has 5 volts across it. Okay? 10 volts from the power supply, 5 volts here, 5 volts here. In some sense, they share the voltage. It's split between the two. So I've got 5 volts across this resistor, 5 volts across this resistor. Here's a question. What current do we see in this circuit? And you know we can break it at any point. We can put this meter any place in the circuit that we want. We'll break the circuit. We'll put the meter in. What current do we measure? We'll give you some choices. Well, if there's 5 volts across each of these resistors, we can apply Ohm's law. Ohm's law, the current is equal to delta V divided by R. The current is equal to 5 volts, which is the voltage across this resistor, divided by the resistance, which is 1,000 ohms. And so I predict 5 milliamps. And in fact, that's exactly what I measure. There's 5 milliamps through this circuit. And it's because the voltage across each one of these resistors is less than it was before. And so the current in the circuit is less. But now think about this. From the point of view of this power supply, it sees it's putting out 10 volts. It sees it's providing a current of 5 milliamps. So the power supply doesn't see that it's hooked up to 2 resistors. Suppose the power supply only saw one resistance. In fact, that's what it sees. It sees a load. It looks like a single resistor here. What is the value of the single resistor that we could replace it with? The power supply puts out 10 volts. It's supplying a current of 5 milliamps. And we can use Ohm's law for this case. Ohm's law for this case says resistance is equal to delta V divided by I. And in that case, we get 2,000 ohms. And so we could say this. The equivalent resistance of this circuit is 2,000 ohms. 1,000 plus 1,000. And so if I have 2 resistors connected in series, the equivalent resistance of the two is just the sum of the different resistances. But there's another type of circuit which we want to look at in this chapter. This is a series circuit. Now I want to look at a parallel circuit. In parallel means this. It goes through them both together. So what we do is we take the 10 volts from the power supply, hook it up to the meter. I still have 10 volts right here. And I have 0 volts right here. This resistor is now hooked up to 10 volts because I have 10 volts at this side, 0 volts at that side. Then the second resistor gets hooked up in parallel. This end gets hooked to 0 volts, this end gets hooked to 10 volts. And so now the 2 resistors are connected in parallel. It's a very, very different type of circuit. Each one of the resistors sees the full 10 volts. There's 10 volts across this one, there's 10 volts across this one. There's 10 volts from the power supply. Question. In this situation, right here, what is the current through this resistor? It's got 10 volts across it. What's the current through it? We'll give you some choices. Well, the current is just delta V divided by R. It's the voltage divided by the resistance. The voltage is 10 volts. The resistance is 1,000 ohms. And so the current is 10 milliamps. So I've got 10 milliamps through this resistor. But what's the current through this resistor? It's 10 milliamps. It's hooked up exactly the same. So what is the current measured by the meter? Because the meter doesn't measure the current in each individual resistor. It measures the current in the circuit as a whole. The current comes out of the power supply, goes into the meter, splits, goes through both resistors, back into the power supply. What is the current measured by the meter? We'll give you some choices. Now, let's take a look. The current comes out of the power supply, comes into the meter, and then it splits. 10 milliamps goes through this resistor, 10 milliamps goes through this resistor. So how much has to come in? 20 milliamps. This is an application of Kirchhoff's junction law. So now think about this. The meter is measuring 20 milliamps in the circuit. The power supply is putting out 10 volts. So from the point of view of the power supply, what is the effective resistance of this circuit? 10 volts, 20 milliamps. What is the effective resistance of the circuit? These things look like a single resistance to the power supply. And what is that resistance? We'll give you some choices. Well, the power supply thinks it's driving a single resistance that draws a current of 20 milliamps for a voltage of 10 volts. And so that implies a resistance of 500 ohms. And so the resistance of these two resistors connected in parallel is less than the individual resistances. And that's always the case. And in this case, it's just half. That's one of the special cases for parallel combinations that we'll see in the chapter. Now, these are two simple circuits, a simple series circuit and a simple parallel circuit, but we will look at much more complex circuits, which are made of many parallel and series elements. You can use the same rules, and then we'll look at one more piece, which is what happens when you add a capacitor into a circuit. And that provides us the opportunity to do something very special, as we'll see in the next segment.